very few have actually paid good attention. So that's class, guys. I'm more just warning that my patience is kind of running out. I'm more just warning that my patience is kind of running out. So not that it's against you guys if I do get frustrated. It's just been my smartboard's not really working. You guys notice I pick up a pen and it's supposed to be like, yeah, you want a pen? No, it's not red, it's blinking green. I have no idea what it means. Oh well. But we'll do what we can. What do you guys see when you see linear approximation? Tangent line. Good. You see linear approximation, you see tangent line, and what do you see right below? Tangent line. But that's not like the normal form of a tangent line, is it? Or is it? It's just a little, yeah. How is it reformatted? What is capital L of X the exact same thing as? Y. Right? And then what's F of A the exact same thing as? Y1. And what's F prime of A the exact same thing as? So this literally is just a tangent line with y minus y1 equals m times x minus x1, or y minus f of c plus y minus f of c equals f prime of c times x minus c. They just threw in a's instead of c's. That's what Lorenzo was trying to say. Okay. So at x equals a, the tangent line skins, and the way we make it skin is by establishing its slope as the derivative at that point and plugging in the point of tangency as its y minus y1. Sorry, as its x1 and y1. So the idea isn't super complicated, is it? No. The form is just a little different. And the reason the form is a little different is because then we can use the tangent line to approximate values to where we can say, okay, for points other than A. For points other than A. We could say that f of B could be approximated by L of B. You guys see what the statement is saying? We can approximate f of B by using L of B. L being the line, aka the tangent line. L being the line, aka the tangent line. So what this notation allows us to do is like, sweet, if we want to use a tangent line to approximate, we already have the y value all nice and isolated, and so we can just go ahead and plug in the other side of the tangent line. But remember, this is only going to be a good approximation, or a fair approximation, a fairly good approximation, for B close to A, right? If B is close to A, yeah, sure, I mean, maybe, it's not too bad. It's bound to be close at least for a little interval, true? But then if we get very removed from the point of tangency, well, there's bound to be better ways to approximate. And there are, but we'll learn them second semester, for the most part. We'll see a little bit this semester, but most of the approximation techniques that are better than tangent lines, we have to wait until kind of the end of second semester. So, let's check it. What if they said, find a tangent line approximation of f of x equals 1 plus sine of x at the point 0, 1. Then use a table to compare the y values of the linear function with those of f of x in an open interval containing 0. This example is kind of weird because it's kind of ambiguous. Use a table. What? Let's start off just making me the tangent line approximation. Find me L of x. Go. Find me L of x. Go. The air should turn off soon. Hang in there. Find me L of x. Quick warning, but also opportunity as you guys are playing with the tangent line. I have an appointment for my foot today, finally, at Kaiser. So, and it's like, I have to leave during period 7. And CalcAB has their basic derivative test tomorrow. Do we see an opportunity, kind of like clouds parting, sun shining? What are the CalcAB kids going to want? Help. They're going to want help. Think of 1 or 2 or 3, maybe friends, maybe classmates, maybe teammates, where you're like, ooh, they're probably struggling in calc. You might want to check in on them and be like, hey, do some FaceTiming tonight. Could do some work after school. Not in my room where it's freezing. Maybe like the nice warm senior patio. I don't know. But there is a prime opportunity. I'm going to be here today at lunch for them. I'll be here during most of 7th period for them. But then, I'll be here in the morning because it's a Thursday morning for them. But I won't be here after school. They're going to want some help. Maybe I should even say they're going to need some help. Why don't you guys be that help for them? You don't have a test until next week. Next Wednesday, I believe. Alright, check in your groups. You guys have the tangent line approximation? Shouldn't be too bad, right? Yeah. One plus x? Because it's y minus y1, y minus 1. If you want to do it that way, you totally can. Just you're going to have to kind of rearrange it. But y minus y1 equals m is f prime of 1 times x minus x1. All the L of x does is say, hey, let's go ahead and move to one side. So x plus 1 or 1 plus x addition is commutative. It's okay either way. 1 plus x or x plus 1 either way. This is just in the proper L of x form. F of a plus f prime of a times x minus a. But what are they asking for next? Has anybody even thought about that next part? Make a table to compare the y values of the linear function. Linear function. So these y values, we're comparing these ones to who? These ones. No, that's a linear function. And we're comparing the linear function with. Oh! So we're going to go ahead and make a little baby table. A table around 0, an open interval containing 0, around 0. And we're going to compare, hey, how close is the line to the actual function? Because the linear approximation, the tangent line approximation, linearization is saying, hey, I can approximate you sometimes. Okay, well, let's figure out the sometimes. So let's see, if we're trying to think on either side of 0, at 0, we already know they're the same. That's boring because they have a shared point. They're the same there. Let's go a little bit before, a little bit after, using our calculators in radian mode. So let's see, we could go ahead and try like -1, -2, -3, -4, but don't you guys think that's getting kind of far off the point of tangent? Because remember, look at the picture in the page before. A tangent line is really good, real close. If we get too far away, man, those differences are going to start. Well, basically, the tangent line is going to diverge from the graph. The graph's going to go one direction, the line's going to go the other direction. Well, so maybe we should even do something like -1/2. And see how close, and then maybe 1/2, and then 1, and then 2. Now, if we see 1 and 2 and -1, -2 are way far off, well, maybe we should kind of bring that in a little bit. But they're just curious for how long an interval. Is it a good approximation, or even just kind of judging, is it a good approximation at all for very long? All right, y equals, throw in the function, throw in your linear function, aka your tangent line, aka your linearization. Do we not bring our calculators at all in BC?
I got one.
Okay.
We can share.
We can share.
I have it, but it's out of battery.
Well, E for effort.
Because my charger is stuck.
Do you want me to charge it for you?
I mean, like, I don't literally charge
Is
right
that
now.
a new calculator program?
We never use our calculator. You don't lose anything.
Yeah, they updated it. It's kind of weird. Not a huge fan. But that's okay. Like, it's kind of nice in some ways and kind of weird in other ways. Ooh, that's like far off. -1 and 0.09? I mean, maybe it's not far off to you. It looks kind of far off to me. Oh, that's a little closer. 0 and 0.5 or 0.15. Okay.
Oh, wait, up there.
Ooh. Ooh, I see it, don't you? Maybe I'm going to throw in another one. Ooh. Look at how close that they approximate. I don't remember which one's which. Is my line my line's the blue and my red is the function. But guys, for values, like, look at that. That's like 3 decimals of accuracy, right?
Yes.
And then 2 decimals, and then 1 decimal, and then, oh dear. Well, I mean, we could plug in 0, but remember, that's where it skims. That's where it's perfect, so that's no fun. But then, I mean, I'm guessing I'm going to see the exact same thing on the other side if there's some sort of symmetry. Oh, yeah, okay. So it's somewhere different, but I'm still seeing almost 3 decimals of accuracy. If I round it, it'll be about right. So you guys see a window where it seems to pretty well approximate, right?
Yes.
And then, okay. I mean, we can't just go ahead and say, okay, well, what if we had 5 instead? I mean, it's going to get farther and farther and farther, like 20 instead. Like, it's not even close. Your x plus 1 is kind of like, and your curve's, well, doing something far different. And we know our curve is trigonometric, which means he's only going to be, like, wavering, whereas the line's going on forever. So, of course, they're going to go different directions, but there for a little bit. There for a little bit. It was a pretty good approximation. Like what you should be able to expect. Tangent lines, great for a little bit. Tangent lines are great for a little bit. So, can you guys use a tangent line to find the approximate what both of those are without using a calculator? How could I be asking you to approximate? Just a second ago, we were approximating 1 plus sine of 0.25, or 1 plus sine of 0.5, or 1 plus sine of 0.125. By plugging in 1 plus x. So how am I expecting you to know what the square root of 123 is? I don't. I don't expect you to know what the square root of 123 is, but I do expect you to think of, what's my function? Rad what? Rad x. And what would be the good at? That 123 would be within the good approximation, right? 121? Go for it. I would use a tangent line at 121, the square root of x. Ooh, and maybe for the next one, I would use a tangent line to the function. Oh, I can't give it away. You guys do it.
plus prime of it. The derivative is like 1 over 2 square root of x.
But
That's like,
when you're asking
wait, like these ones? Yeah, 120.
And then
Square root of 1.
No, I'm just kidding.
Oh. I mean, cause like, you should know from 1 to 12. There are things like, or 1 to 12.
Are you using this number?
Second deferred times first.
Wait, why are you doing power?
Oh, and then you just go in.
Or 242. 121 minus 242 is then you told me the wrong parameter. You told me the wrong parameter. Yeah. How's that close to you?
1 over 1,062. Minus 121. Yeah, if you want to simple. Oh, wait, no, I'm not. Oh,
That was crazy.
Oh, I bumped.
You plug in the 123 and that's
Whoa.
revolutionary.
I didn't, what?
700.
Wow.
Infinity to the infinity.
$11.09090909. What is the actual square root of 123? 11.0905. But wasn't it a good approximation?
Yes.
Both of them would say 11.091.
How did you, how did Lorenzo get x equals 1?
Oh, because remember, tangent lines are really good as long as they're close to a point of tangency, and the only nice point of tangencies that I know are perfect squares. So 100 was going to be pretty far away. 121 was a lot closer. 144 once again would be pretty far away.
It has to be close to that number.
To be a good
So it can't
approximation.
be like 10 squares.
To be a good approximation. Now, if I give you something like the square root of 117, do you have a really great way to approximate that? No, because 117 is pretty far away from the perfect square of 100, or pretty far away from the perfect square of 121. What is this? Not that far. Maybe if I did like 112. It's going to be kind of rough as to which tangent point to use. I mean, you could still approximate it, but it wouldn't be as nice. It wouldn't be as close. It wouldn't be as helpful. Why have I randomly, but not randomly at all, chosen the cubed root of 26? Close to the cubed root of 27. And AJ, cubed root of 27 is equal to 3. So go find me the tangent line approximation of the cubed root of 26, which is very close to the cubed root of 27, which is perfectly equal to 3. If we choose a point of tangency that we don't know the nice root to, the square root, the cubed root, we would have a radical in an approximation for a radical. That doesn't help if we're not any 26 minus 27 because I'm plugging in 26. And minus 27 is my x minus x1.
42. Is this the number one?
Oh.
I'm scared. Okay. Bro. Math is awesome. You should know now. Ask him like tomorrow. Like ask your physics class. No, ask me tomorrow. Be like, I don't like it. Ask me in March. You're lying. It's a fact.
Ooh, it's 296, 296, 296. You guys get the same thing?
Yes. What? I'm gonna
And what's the actual? 2.962. 496. Okay. 962. Not too shabby. So what is that? That is approximately the cubed root of 26. Because once again, the L of, ooh, that doesn't work.
Some of it.
L of 126 is approximately the cubed root.
Of course.
Sorry.
I
Okay, so the cool party trick as far as with square roots. Yeah, a little bit. Wait a minute. What else is here? Oh, wait a minute. Okay, so maybe this section isn't only tangent lines.
That'd be nice.
What else is it? Differentials. Differentials. I thought those were, delta y over delta x's of tangent lines. So since we're talking about tangent lines, can't tangent lines be thought of in other ways too, or be used in other ways too? Tangent lines. Dy over dx. There's my dy, there's my dx. A delta y and a delta x of the actual tangent line itself. How can that be of any use? Well, the same way I can use a tangent line to actually approximate a function value, I can also use the change in y of a tangent line to approximate the change in y of an actual function. So dy goes up to the actual function, whereas something like this, using the exact same dx, would be a delta y. Delta y says, okay, go over the same dx, so technically delta x and dx can be the exact same thing, because they're both just going over. But delta y says, let's go up to the actual function, the y goes up to x, dy says, let's go to the tangent line. So that's dy, now, not when you're very diverged from the original, it's going to be kind of a worse and worse approximation, but for values close, maybe dy can approximate delta y, which means maybe who dy equals, which is f prime of x dx, maybe who dy equals, which is f prime of x dx, can approximate delta y. So, first of all, how would you just find dy? If you're going to maybe use it to approximate something, how would you even find it? Well, who's dy of this guy?
10 sine.
Do you see how I gave you a really fun
10
example
sine
of
pi
a
x cosine pi.
I'm hoping that you're going to be tutoring calculus AB kids. You have to know their chain rule and their trig rules, and don't get tricked by the trig notation rules.
I fool.
Welcome to dy dx game. I should wear the sweatshirt.
You guys agree? Do you agree?
Yes.
Are you sure? You bring down the 2, you make it a 1, and you have a u prime at the end after doing the cosine. So 2 times the 5 is going to be 10 sine of 5x cosine of 5x times dx. How about the next one?
So 3 to the 2x.
Woo-hoo-hoo.
Is this close?
Are you going to beat me on this one? I'm not so sure. Oh, for this one?
Oh.
Well, I made it look kind of nice. So it's y prime, which is 2u,
I do squares and triangles. I think that would make something happen.
times u prime, which is cosine v, times b prime, which is 5. I just did the 2 times 5 is 10. And then my u was my sine of, and then cosine of. We're just deriving, and see it? You guys remember your b to the u formula? You're welcome.
Oh, I didn't look at that.
I was just sitting there waiting for you, as it was sitting there during the forever quiz today. Dark out 36. But I have to be equally fair. I'm sure they do. I'm sure they do. They'll probably be like, but I heard period 1 got to leave it out. So I'll just leave it. Whatever.
Period 1 does not represent.
I mean, it was a quiz on 5 different cards, 6 different cards, but yeah, I accidentally left it up.
Period 1 is just like bro.
Yep.
I said it earlier.
Did you guys get your ln of 3? Did you do your green rule trick?
No. I did take that one.
Don't use plastics.
I just didn't backdrop the
Oh, that makes sense.
She said she got the same thing. She just
I didn't backdrop.
backdrop the 3 to 2x.
Oh, okay.
You guys agree?
Yes.
Yes.
So you do know your derivative rules.
I actually remember.
Okay, so that's in the section. Oops, I don't want that. That's okay. We'll see what happens. What else? Woo!
Oh.
Well, hold on. Follow directions. Okay, so y equals x squared. Got him. Find dy. Oh, this is an easy one. What's dy?
2x.
dx. Find dy when? Uh-oh, there's a such that. No big deal. When x is 1 and dx is 0.01. Oh. What is that?
We derived.
Plug it in. 2 times 1 times 0.01. Isn't that 0.02? Oh. That's fun. Compare this value with delta y. Ooh. Who's delta y?
Is dy.
No, delta y is approximately dy. Who's actual delta y?
Approximately f prime.
Isn't delta y f of x plus delta x minus f of x?
All over.
Difference quotient.
I don't know.
I don't remember that.
Compare this value with delta y. So delta y, wouldn't he be f of 1.01 minus f of 1? Wouldn't that be 1.01 squared minus 1 squared? Are you guys in agreement?
Yeah.
Because this is how far off we were from the 1. So like kind of with the tangent line, how we go just a little bit off from the tangent line and try to think about things. They're saying, what if we need to figure out the difference between these two? We were just a little bit off. How far off? Oh, okay. So he's 1 and he's 1.01. Then how did I get this expression? Yeah, who's f of x? Oh, it's x squared. Oh, okay. So they're looking for 1.01 squared minus 1 squared. Now, could we have done? Yeah, I suppose so. Oh man, 1.01 times 1.0. So I have 101, and then I have 0, and then I have. Huh. close were we?
Pretty close.
Yeah. Pretty close. Which one was easier?
First one.
The derivative. Oh, derivatives are easier than normal math. That's fine. Sometimes. But what made this a pretty good approximation? Well, I was still pretty stinking close. You guys agree? So, this is a quick reminder of how this could get really, really weird. As soon as we start talking about how dy can approximate delta y, then not only can delta y, which this is all like the snappiness of, okay, but I just wrote down delta y was like a difference quotient numerator, f of x plus delta x. Oh, that's right. The difference quotient is just a slope formula. And slope is delta y over delta x, so I guess the top had to be delta y. Anyway, that's okay. Error propagation, we can approximate delta y, who could be found by using f of x plus delta x minus f of x. dy can approximate that, which is kind of nice and kind of cool. And if dy can approximate that, not only can dy approximate delta y, but the ratio of dy over y can approximate delta y over y. And the ratio, that could be something like the percentage. So not only could we figure out how far off the measurement is, or the approximate for the measurement error by dy, we could also put that over y and also figure out the percentage, or the error percentage, the error propagation percentage of change. Oh, there you go, percentage of propagated error. By just doing a quick little ratio. So a couple things that we can do now that we have, like, oh, sweet, dy and delta y, that's like an approximation thing. So can't we kind of call this section the approximation thing with the first derivative? Because we're using the first derivative to get a tangent line to approximate y values. We're using the first derivative, well, the dy part, to approximate change in function values. And then we can use a ratio of the derivative over the actual to approximate the percentage change. But still, we're using the first derivative to approximate stuff. We're using the first derivative to approximate stuff. We need to grade our optimization homework, but here's an example I just snuck in from the end of notes that is solved out in your book, but we might not make it through the entire thing, but can you guys at least help me identify what's given? Because remember, we always read a paragraph, try to pull out the mathematical meaning as far as what we're used to with variables, etc. So what is all this stuff? The measured radius of a a ball bearing is, oh, look at him, he's such a little baby pepper. Yep. So the radius is, oh, r equals 0.7. Okay. If the measurement, 0.7, is correct to within 0.01, depending on whatever tool they use to measure it, and the tick marks, etc., they're assuming you've gotten within 0.01 of an inch. Estimate the propagated error in the volume of the ball bearing. Whoa, volume? Oh, to find volume, wouldn't you have to use radius? And if there was a certain radius error or a possibility of error in the radius, wouldn't that kind of be compounded as you used it in volume? So wouldn't we have to think about, first of all, a volume formula of 4/3 pi r cubed, which is true for any spherical solid? So couldn't we go plugging in what is v of 0.07 or 0.7? The problem is, hold on, if my v, I could plug in 0.7 to v, but I'm trying to figure out how far off. Oh wait, how far off? I need to find the change in v. Oh, the change in v when plugging in 0.7 and plugging in up to 0.0701. Oh, no, 0.71. Because basically, if 0.7 is correct within, doesn't that mean that my actual is going to be somewhere between 0.69 and 0.71? Does that make sense? Because it's within that much. So my change in my r, my change in my r is equal to 0.01, which is the same thing as dr. What am I trying to figure out? how far off, oh, which could be approximated by, otherwise you'd have to be plugging in all the decimals between 0.69 and 0.71 to your volume and see how far off it got. Or maybe just plugging in 0.69 and 0.71. Do you really want to cube 0.69? Calculator, the whole point is that we're not using our calculator to try the words out. So, can we just do dV by, when we bring down the 3, those are reduced 4 pi r squared dr? True? Couldn't this approximate delta t if I plug in my information of r is equal to 0.7 and dr is equal to 0.01? So then I would go ahead and plug in and say, okay, so I have 4 pi times 0.7 squared times 0.01. So instead of having to cube these nasty decimals and figure out the range, what was in 0.07 squared, just 0.49? Oh, that's not too bad. Oh, and doesn't 0.01 just move a decimal place 2 places to the left? Well, that's not too bad. Can't I go ahead and just multiply that and get, well, not super gorgeous. But I would have a 6 and carry the 3, and then a 16 and 9. Boop. Now, if they want a percentage, we would go ahead and take that and divide it by the actual volume of. So if they wanted some sort of percentage, we would take dV over V, which would be our 0.0196 pi all over. We'd have to actually plug in our 4/3 pi times 0.7 cubed. Because that's how far off our volume could be, and then compare it to the actual volume and see is that a big change, or is that a little change, and a little bit of error, or a lot of error. That's if they wanted the percentage, but I think they just want the propagated error, and the propagated error is just the approximate delta line. Oh my goodness, we had too much fun with the linearization section. Shouldn't have done the whole example. Oh, that's okay. We still have 2 minutes. We do have your section 5.4 that some of you got stuck on, to be totally honest. If you got stuck on it, what am I doing right now? Recording. And what am I recording? Solutions. To number 2, for instance, where it tells us our final largest area for dimensions. And solutions for number 14, which talks about, I don't know, position, velocity, and different maximum heights, etc. Or the solution to number 50 having to do with profit. Oh, and that was it? Okay, you guys had the odds to struggle with last night. Now you have the even solutions to peek at tonight. Remind me when we're grading to grade both homeworks tomorrow going over questions. Sound good?
Yeah.
All right. I'm pausing the video. People who didn't make it to class today, hope you watched it.